Hi, and thanks for watching this video, which is about my homebrew computer. I haven't done an update for a while, but I did in the past try to look at benchmarks. I thought I would do something a little bit more detailed, which is why what I've got here is three bits of presentation on this video. One is the homebrew computer on a regular TV LCD screen outputting composite video. And here is the another view of the homebrew. So you can see that I'm actually running it on real hardware rather than emulation. And then on the right hand side, I wanted to give a reference to what we mean by benchmarks and where I got my benchmark ideas from is from the day, back in the day. In fact, in the late 70s, I didn't realize how long these things were been around. And the Rugg-Feldman benchmarks have been used in quite a few magazines, in particular PCW in the UK. I remember in the early 80s reading their reviews of computers and seeing the benchmarks that those computers achieved using the equivalent of the Rugg-Feldman benchmarks from 77. So I thought this was a very interesting um, set of benchmarks. There's the you can see the URL here in terms of the Wikipedia page. What's interesting is the table down here, which shows some results achieved from computers from back in the day, and I wanted to use this as a reference to see what could my homebrew achieve. Of course, my homebrew is a modern 6502 build. Yes, it's a bit of a mess on a breadboard. It looks like that, but it does run at 5.36 megahertz, which is quite a lot faster than the first 6502 machines, which came out in the mid late 70s and all the way through, in fact, into the mid 80s, early 80s. They were ran typically at 1 megahertz or maybe 2 megahertz. So clearly, I've got a much faster CPU, but on top of that, the programming language that I've developed for this computer is called dflat. And dflat is a basic like interpreted language, but with some optimizations to make it as fast as I could for this constraint of memory and CPU, and with some modern language features, procedures, etc. So it's optimized, and the biggest optimization, or I would say rather advantage that this basic has, is that it's integer only. So if I try to print 5 divided by 6, I just get 0. If I do 5 modulus 6, then I see the remainder of that division. So it's integer only, which makes it very fast. But back in the day, there were also integer only basics, and we'll go into a couple of those famous ones as part of this. So before I continue, I think I need to change the color of this to make it a little bit more readable. I wonder if that's a little bit easier to read. Anyway, I hope it is. So on my storage here, I've got a folder called test bench, and I want to first load the PCW bench here. So I'll load that PCW bench.prg, and then if I show you the procedures that are in here, and I'll go through them. But one of the challenges I have with this, if I list test one, and then we'll go and look at what that looks like on Rugg-Feldman tests. So test one is simply a for next loop from 1 to 1000. And let's just quickly look at one of the benchmarks as a preview. On the Apple, it takes 1.3, on the Apple II with integer basic 1.3 seconds. Now, that is quite quick, but let me show you how that looks on using my basic. So if I was to execute test one, oops, like this, and then maybe I'll try and use my stopwatch to try and do a start and a stop. So I'll press enter, and it's just too fast. I'll try it again. It's just too fast for me to be able to actually react in time. It's not going to be very accurate. So what I've done instead is to have one called bench 20. So if I load bench 20, and then I list test one here, I've got to remember my own syntax. Is test one. Instead of it being from 1 to 1000, I've done the loop 1 to 20,000. So that'll give me a chance to be able to actually react to the start and the stop and do the hand timings with a little bit more accuracy. So let's just go through the tests, shall we? So as you saw, test one is a simple for next loop. Let's look at test two, because oh god, let's look at test two, because test two is, you can see here, is a repeat until loop, and that is not what the Rugg-Feldman tests specified. So test 2 is adding 1 to k 1,000 times, and if k is less than 1,000, then it keeps going back to line 500. Unfortunately, or maybe one could say fortunately, but it's certainly by design, my programming language dflat does not have any ability to reference line numbers, so there is no goto or gosub. The line numbers are purely to store commands in sequence in memory. So I do have a repeat until construct, and that's what I've had to use here. So I'm using repeat until, but it's also counting to 20,000 to be able to give me a chance of reacting to the timing. So then let's look at test 3. So this is similar to test 2, but now it's doing some calculation, just saying let a equals to k divided by k times k plus k minus k, just exercising a few mathematical operations, and that's what I'm doing here on line 390. So that's pretty accurate, or equivalent, let's say. And test 4 is adding, it's doing some constants. Rather than using variables, it's using constants. So it's testing the conversion of constants in BASIC. Actually, in dflat, all of these constants are already tokenized, so it should be virtually the same as the previous test. Test 4 should be very similar to test 3. And then test 5. This is calling a subroutine. Now, in the Rugg-Feldman tests, it goes subs to a routine which immediately returns. Again, I can't go sub to a routine, I have to invoke a routine. So line 620 invokes a routine called sub. If I list sub, you'll see it just immediately ends, and so it will return. So it's again equivalent, but not exactly how the Feldman tests are specified, but I just don't have the constructs. So let's look at test 6. So now in test 6, we're dimensioning an array, we're doing some calculation with constants, we're going to a subroutine, which just returns. And then there's an empty for next loop, 5. Okay, and that's what I'm doing here. So that's equivalence. And let's list test 7. And this is the last test that I'm able to use. But here it's dimensioning an array on the Feldman test or Feldman test. It's doing the same calculation, but then in the empty loop, what was an empty loop, it's now assigning a array element to the calculated value and then looping around 1,000 times. So I'm doing the same here on test 7, except like all the other tests, I'm going up to 20,000. So that's basically the benchmarks. And although this video is starting to get long, I guess what I'd like to do is just start executing some of these tests. So let's try test 1. So it's going to 20,000. So let's do that. You can see that. So about 2.59 seconds. I'm not going to do a multiple runs. It's going to take too long. Now that's 2.5 seconds for 20,000 iterations rather than 1,000. So we need to divide 2.59 by 20,000, which even with my maths, I think that is about 1.3 if I divide by 2, and then I need to divide by 10. So it's about 0.13 seconds to do 1,000. That's how I'm scaling it down. I think it's broadly correct to do that. So if I then try and compare that with some of the basics from the day, I can see that it's 10 times faster than integer basic. There was his original basic. My first computer, the Oric 1, see what that is because it's here somewhere. Here it is, 1.8. So 0. So way more than 10 times faster than my Oric 1. And the Porsche of the UK 80s 8-bit scene was the BBC Micro. So let's have a look. BBC Micro, 0.8 seconds, so it's pretty quick. It's 2 megahertz 6502, but 0.8 seconds is still several times slower than my homebrew computer. Let's try test 2. Let's go here. I'm going to reset this. Go. So that's 8.08 for test 2. Divide by 2 makes 4.04 seconds. And then divide by 10, which makes about 0.4 seconds for 1,000 iterations. So if I look at 0.4 seconds versus 3.1 for Apple Integer Basic, so it's not 10 times faster this time, but it's still a good 8 times faster, 7 times faster. Compared to the BBC, it's about similarly about 8 times faster. Compared to I used to have an Atari 800 XL as well, which I really love that computer. Now that is huge, a huge difference in speed. Instead of 0.4 seconds versus 7.3 seconds, that's like nearly 20 times, 18, 17 times faster. More than 10 times faster, 20 times faster than a Commodore 64 to do that test. More than 10 times faster than a ZX80, which was integer, and yeah, 20 times faster than a ZX Spectrum. So the basic is extremely fast. One of the interesting basics that I've spotted is this ABC. It's only a 3 megahertz Z80, which is actually quite slow by Z80 standards. But look at the speed of the basic, 0.3 seconds and 1.1 seconds. So even though my homebrew is significantly faster than other 6502 machines, it's only a couple of times, or two or three times faster than the ABC, which is interesting in terms of how that interpreter must work. And this is the integer version as well, so it's like for like in terms of not using any floating point. But even the floating point version down here, you can see that the using single precision is very, very quick compared to nearly every other basic. I think only BBC Basic comes close to it. In fact, I think it's actually quicker than BBC Basic overall. But yeah, that's pretty impressive. The ABC series of computers with their single precision. The BBC actually had a higher precision than this. It's actually more like this benchmark. But still, I think that's a pretty interesting computer, which I don't know much about actually. So I think what I'm going to do is, rather than let you wait through all the rest of the tests, I think I'm going to do the tests and then come back to this. So let me just let's just pause this. Yeah, so I'm going to pause this, run all the other tests, and then come back with the results. Okay, I'm back. The other, I did all the other tests. So if I show you test 7 or test 3 rather, this was doing the calculations, and that was. Let's have a look. Let me go back to my results screen. That was test 3 with 1.14 seconds for scale down from 20,000 iterations to 1,000 iterations. If I look at test 3, 1.14, again, that's several times quicker than the integer basic of Steve Wozniak's. Now, of course, let's admit here the disadvantage of the Apple II at 1 megahertz compared to my machine, which is 5.36 megahertz. But if I calculate correctly, so if I use the calculator and say, well, what is 1.14 divided by, or rather 7.2 seconds divided by 1.14, that is 6.3 times quicker. So dflat is still like for like. If I clocked it down at 1 megahertz, it would still be a little bit quicker than 7.2 seconds, which I'm pleased about. That's nearly 50 years after Steve Wozniak wrote Integer Basic. I've managed to slightly do better than his basic. So it's not really covering me in huge amounts of glory in all that time, but at least I've made some progress on a personal note. And then let's look at some of the other results. Test 4 was also 7.2 seconds for Apple Basic, whereas for, it's interesting actually, it's slightly faster using constants. It's 1.1 seconds, just over 1.1 seconds for 1,000. So it's actually more than 6.5 times quicker. Again, comparing with some other basics, so it's 7 times quicker than BBC Micro, ZX Spectrum. It's a lot quicker. Commodore 64 as well. Similarly, it's like 15 times quicker. 20 times plus quicker than my Atari, and my Oric, which I always like to compare things against. It's 25 times plus quicker on this benchmark. Then going to test 5, 1.24 seconds. So test 5, 1.24 seconds. Yeah, it's really going great guns. Test 6 is 2 seconds versus 18 on Waz's computer. So 16 times, sorry, 9 times quicker. And then test 7 is 3.2 seconds from my measurements, so versus 28 seconds here. So again, 8 times quicker. Of course, again, let's remember the clock speed is significantly lower on the Apple II. So I thought that would be an interesting aside for folks to get an idea of how the homebrew performs against some computers from back in the day and the built-in basics that they came with. And yeah, hope you found that interesting, and thanks for watching this video.